Hello AP Chemistry, and welcome to 7.2 Buffered Solutions part I don't know because they keep on going, but I promise it will end at some point. Then we're going to talk about how to make a buffer. So we talked about what a buffer is, right? So a buffer is something that's composed of a weak acid and its conjugate base, or a weak base and its conjugate acid, right? Because we have, in that scenario, an acid and a base coexisting in a solution, not consuming each other, what that means is we can add strong acid or strong base, right? And they can be consumed, right? And the overall pH doesn't change much because, going back to what we talked about previously, right? Ka is a constant, so as long as the ratio of Wa or Ha, however you want to say it, weak acid to its conjugate base doesn't change significantly, neither does the concentration of H3O+. Therefore, the pH also doesn't change significantly, right? So then that brings us to how do we make a buffer, right? Because obviously we got to be able to do that. We know what it's made of. We know how it works. How do we make one? So let's say we wanted to make a buffer of pH 4.74, and I forgot to write it down, but we're going to make it out of acetic acid, right? So let's go ahead and just, write out that expression because, why not? Good practice. Right, so we have that, right? And pretty much every problem starts the same way, right? We know we have this. Yep, I'm just going to shortcut that because that's easier. Over my HA, right? Which means I also need to know what my Ka value is, right? If you've not memorized it yet. The Ka for acetic acid is, I think, 1.8 times 10 to the negative 5, all right? Now, obviously, we've got to know some information in order to figure out how to make our buffer, right? So, what does this give me? The pH. Right, that actually gives us the H plus concentration that we're looking for, right? So if we just do a little bit of rearranging, right, we know that we can, actually, let's just go ahead and do that real quick. Okay, so when we do 10 to the negative 4.74, this is my hydronium ion concentration in this buffer system. And why is that significant? Right, because that is my Ka, yes? When Ka, thinking about what we've talked about previously, when Ka is equal to H3O+, that means A minus is equal to HA, yes? So if we take all this information and rewrite it over here, if this is 1.8 times 10 to the negative 5th is equal to A minus times, 1.8 times 10 to the negative 5th over HA, right? Then what that means, right, thinking about what we've talked about previously, right, however we want to isolate this, we can go ahead and say, let's say we divide both sides by that 1.8, right? Then we get 1 is equal to A minus over HA, right? And so what's the significance of that? Right, all that means is that we need to have the same concentration of each, right? And if we need to have the same concentration of each, since they're swimming in the same beaker, that means we need to have the same moles of each, however we design our buffer, right? Does that make sense? That's what we're shooting for, right? So if we're looking at our figures, here it says I have 200 mils. Don't mind those exclamation points. That's like a weird thing that came with the app I was using. But anyway, if I had 200 mils of 1 molar, that means I have how many moles? Right, I have 0.2 moles of my acetic acid already present in this beaker, right? Which means that if this is, what must this be? Right, that could be any acetate salt where the cation is from a strong base, yes? So for example, this could be any group 1, or the bottom half of the group 2, because the point is it needs to be the cation from a strong base because that means it has negligible acidity, yes? Must be the cation from a strong base such that it has negligible acidity and will not affect our overall solution, right? So then what that means is I need to measure out 0.2 moles, and I could use the molar mass to figure that out. And then I would take that and add it in here, stir it up with our stirrer, and then I would have a buffer with a pH of 4.74 and equal moles of acetate and acetic acid. Yes, does that make sense? All right, now the other method is technically easier, yes, as in like technical, as in if we were sitting in a lab and we had to do it, it's actually easier. But for whatever reason, it's a little harder to wrap your mind around. I don't know why. But this method would be called partial neutralization. Okay. Now, this is important because obviously that's going to come into play, oh my gosh, right, in the next section when we talk about titrations where we do neutralization reactions, right, and buffers become a big part of our discussion, right? But so let's say that we have 200 mils of 1 molar acetic acid, right, which again means 0.2 moles of acetic acid, right? Now, I need to make a solution that is equal parts HA to A minus, right? Now, first of all, what do I need to add to get that done? Right, acetic acid is an acid, so I'm going to need to add a base, okay? I'm going to need to add a base because if I take CH3COOH and I add a base, like we're just going to say this, right? What's going to happen is hydroxide ions are strong bases, right? They will react completely. And what's going to happen is I'm going to make CH3, COO minus, and water, right? So by adding hydroxide ion, we are going to produce in the solution acetate ion from the acetic acid, yes? So then, going back to our original question, if I must have a 1-to-1 ratio in terms of moles, how do I do this? Okay, I'm going to assume you said the right answer. Of course you did, right? What we're going to do is we're going to add 0.1 moles of NaOH, yes? 0.1 moles of NaOH, right? Now if I look back at my math down here, right, if I were to add 0.1 moles of NaOH, how much acetic acid gets consumed? Right, 0.1 moles. How much acetate ion gets consumed or gets produced? Right, 0.1 moles, which means that in my final solution, right, when this is all done, it will contain 0.1 moles of HA and 0.1 moles of A minus, right? And because it's a partial neutralization and the hydroxide ion is limiting, no more hydroxide ion. Yes, does that make sense, right? That's what will be in the solution when we're done with our partial neutralization. So even though the total amount of acetic acid and acetate is not the same as in the first buffer, right? Both of them will have a pH of 4.74 because it meets the criteria of HA concentration equals A minus concentration. Yes? Does that make sense? I sure hope so. If not, look at this again. Come by and see me sooner than later. Thank you for listening. Be good, and I will see you soon. Bye.